Okay, I'm going to start the class because it's 4 o'clock, 4:01 actually. This is session number 3 for Math 120, mod 2nd, mod 2 for 2021. And we're going to start with a prayer. Father God, I thank you for the opportunity to have this time of class discussion with the dear students, the ones who are joining or the ones who will watch this later on. May you bless all the students in their studies, in their understanding of mathematical principle, and may they be able to use these principles in their lives and in their ministry. Guide and lead us. We pray all these things in Jesus' mighty name. Amen. Hello, how are you?
Hello, Professor. I'm doing good. How about yourself?
Good. Yeah, I can see you're doing good. I can read from your assignment. You're doing very good. Today, before we go to our lesson for this session and the PowerPoint, I wanted to discuss some of the questions that were missed on quiz number 1, or actually from assignment number 3. Not quiz number 1. So let me use my tablet because that makes it easier. Let me go to the share screen. How are you doing yourself?
I'm doing good. I'm a little busy at work, so a little tired, but you know, it is what it is. It's life, but I'm doing good.
Okay, all right.
But yeah, I appreciate you going over it because I was struggling on those 2 questions. So I'm glad we're gonna go over it.
Yeah, actually you did good, but there are some few things just need to be cleared. Let me, okay. Just wanted to make sure that this thing is working, and yeah, that's good. Let me just clean up. Clean up here, and then we go over there. Okay, so let me go to share screen. All right. I'm going to focus on the only issues, the thing that you guys, all of you, have missed. The first 3 questions, you see, in the first 3 questions, most of you got it right, but let me explain a couple of things. The only set, which is, the only one that is not really a set, a well-defined, and therefore cannot be considered a set, is number 2. Number 1 and number 3, they are well-defined, and therefore they can be considered as set. Number 2, and the reason is not well-defined because you see it says the collection of elderly full-time student currently enrolled at SCS. What do we mean by elderly? That's not well-defined. What age do you consider somebody elderly person? So that's the reason. Then questions 4 through 8 were all fine. The one that, okay, number 9 also, you guys all got it right. Number 10, that's the one that number of you had problem. You see, in number 10, the question is this, is giving us a prime in an intersection with B. Okay, then all of it in a parenthesis prime, whatever that comes out. So let's first start from inside this parenthesis. And first, so let's just consider A prime intersection with B, okay? And then let's consider what is A prime. A prime is whatever it is not in A. So when we look at A is, let me write it here, or maybe let me write it here. Set A is B and C, and set B is BCE, B, C, and E. You're right, okay. And the universal set that we have is A, B, C, D, E. A, B, C, D, and E. So when it says A prime, it's saying whatever elements in the universal set that is not in A. So we cross B and we cross C. So A prime is A, D, and E. Okay. A, D, and E. All right. Then we want the intersection of that with B, with set B, meaning the elements that are in both set. And what the element that are in both set, okay, well, B doesn't have A, so we cross that. Doesn't have D, so we cross that. There's E here, and there's also an E in B. So the only one which would be the intersection of A prime and B would be E. Okay. Are you so far clear? Okay. So, but remember, so we find A prime intersection with B is equal to set has only one element, E. But the original question is asking us, puts that whole thing and primes it. Meaning, so if we put this whole thing and prime it, so what I'm saying is whatever in the universal set except E. I don't want E. So the answer would be A, B, C, and D. That's the answer.
Okay, so I think, so I got E, but I didn't go the extra step.
Yeah.
Okay, all
Yeah,
right.
you got to remember that little thing here.
So the prime basically means that it's everything except whatever.
The one that is here, which would be A, B, C, and D. Okay. Then
now one quick question. So when we do something like this, it's always going to be the universal set that we're using, right, to cross off?
Yeah, the universal set is given to you whenever you want to find prime of whatever set you are looking at. You need to go to the you need to look at that set and the universal set and pick up the element that are not in, like, let's say, in set A, but they are in the universal set.
Got it.
All right. Okay, that was for question 10. Question 11, you guys, all of you guys got it right. Let me see. Question 12, and remember, just, okay, yeah, 11 was right. Question 12, I think maybe it was you.
I think I got that one wrong.
Yeah, you multiply it by 100 by 10 to power of some number. or power of 16 to power of some number. You don't need to do that. Let me you see, let me do this. Okay. When you look at that, the question 12, it gives us these sticks, 1, 2, 3, 4, and it says each stick is 1. So the first one, actually there are 5 of them. So the first one would be 5. That's it. The second one, we have then this symbol and these two. Now that symbol, according to our the guideline that they have given us, means 10 in the Babylonian numerical system. So it's 10 plus 1 plus 1, which is 12. That's it. Okay.
So I think what I'm doing is I'm multiplying it. So I don't know. I guess maybe it's because I seen one of those videos of Babylonian numerals. Isn't the Babylonian numeral base 60?
But okay, but look at the diagram that is giving us here. So when it says it gives us, it says just go by that. It says when one stick is equal to 5, that symbol equal to 10. So just go by that, and they are all, in one row actually. Okay, so like the third one, let me write it. So you have 1, 2, 3, 4, and then 1, 2, 3, 4, 5. So you have 4, 10, which would be 40, plus 5, 1, which would be 5, which is 45. Okay.
Okay. Yeah. So I think where I'm messing up. So then I don't need to multiply it by the power or anything like that.
No. Unless the question tells you the problem is telling you and asking you to consider that. For example, when we come to question number 14, we see that. Okay, then the question number 13, everybody got it right. Number 14, let's go there. Let me clean this. Okay, when it has this symbol and then that oval shaped thing, and remember we always go from bottom to their positional system is kind of vertical, going from bottom to top. So, and those oval system is equivalent to 0, and this the line is equivalent to 5. But here you see, remember in the Mayan system from the very beginning, we needed to multiply by 20. That was kind of crazy last time. Remember, I forgot about that. So it's 5 times 20, 100. 0 times 20 is 0. 100 plus 0 is 100. So that the answer is 100.
Okay, that makes sense. And so I think where I was just messing up on that number 12 is for some reason, I was thinking it was base 60 and I multiplied it.
No, unless we say it if we ask you if it's required to do that, it will be mentioned.
Okay,
so in the question. Yeah, if it's not mentioned, just go by whatever symbols and numbers that they gave you.
Okay, all right, that makes sense.
Okay, all right, let's clean up here and go to our PowerPoint. And if you guys, by next week, if you guys could choose your chapter that you're going to do your PowerPoint and your presentation, I would appreciate that.
Do you want us to just send you an email or?
Yeah, just send me an email. That would be fine. Or you can even post it on the course bulletin board, and
Okay.
it would be fine. And there are only 3 of you guys, so you have lots of choices.
Okay.
But it would be first come, first base. So if you choose a chapter and another person choose the same chapter, if you chose it first, you will have the chance to do that chapter. Let me see. And next week, because yeah, we can do it. It doesn't matter. It's next week would be the night before Thanksgiving, but that's okay. We can do it. It's okay. But if you, for whatever reason, if you didn't want it to come to the class, I understand. I know it's a busy time for everybody.
I'm gonna try to make it, but I'm gonna be traveling. So depending on where I'm at, if I'm at a hotel at that time, then I'll get on. But if I'm
Yeah,
driving,
yeah, don't worry about it. If it was difficult, there is a recording from last year over there, so you can watch the lesson from last year. So don't push
I'll
yourself.
let you know either way. I'll send you an email and let you know ahead of time.
Okay, all right. So let's go to our PowerPoints here. Okay, and now we want to deal with number theory and real number system. And let me make this. I think it's this thing here. Okay. All right. We use number theory is a study of numbers and their properties. Numbers are used to count. The one that we use to count are called the counting numbers or natural numbers, because we usually begin counting with the number 1. The set of natural numbers begins with 1 and is this is how we denote it. It's n in a parenthesis in those braces 1, 2, 3, 4 to infinity. Any natural number can be expressed as a product of 2 or more natural number, known as factors. For example, 8 is a product of 4 times 2 or 1 times 8. 4 and 2 will be the factors for number 8. Or here, 2 times 4 or 8 or 16 is 4 times 4, 19 times 1. These 19 and 1, these are factors or prime numbers. 4 is not a prime number because 4 can also be written as 2 times 2. Numbers 1 through 1, 2, 3, 6, and 9 and 18, these are all factors of 18. What that means is each of these numbers divides 18 without a remainder. When you divide 18 by 3, you get 6, and there's a remainder is 0. We talk about divisibility. If A and B are natural numbers, we say that A is a divisor of B, or A is divisible by B, or A divides B, symbolized by a vertical line B. If the quotient of B divided by A has a remainder of 0. If A divides B, then B is divisible by A. Or so we write it this way, other way around. For example, 4 divides 12 because when you divide 12 by 4, you get a quotient of 3 and a remainder of 0. So we write it 4, bar, and 12. Every factor of a natural number is also a divisor of that natural number. For example, 12 is one of its factors. 12 its factors are 4 and 3. That means 12 can be divided by 4 and 12 can be divided by 3 and there will be no remainder. Now, don't confuse when we use this bar with a sign of division. In other words, A bar B is different than A slash B or A divided by B. A bar B means A divides B, but A slash B means A divided by B. We shouldn't, just careful about that. Now, we come to primes and composite numbers. Every natural number greater than 1 can be classified either as a prime number or a composite number. Now, a prime number is a natural number greater than 1 that has exactly 2 factors or 2 divisors, itself and 1. For example, 7 has only 2 factors or 2 divisors, itself and number 1. The 7 divided by 7 is 1, 7 divided by 1 is 7, and remainder is 0. Composite number is a natural number that is divisible by a number other than itself and 1. For example, 8 is a composite number because you can divide it by itself. 8 divided by 8 is 1, remainder is 0. You can divide it by 1, and you can divide it by 4, or you can divide it by 2, and again, you get remainder 0. So that's a composite number. Number 1 is called unit. It's neither prime nor composite. Now, for example, if you want to find the prime numbers less than 100, this is a way to do it. You cross out 1 since 1 is not a prime number. You circle 2 because 2 is a prime number. 2 can only be divided by itself or 1. Then cross out all the factors or multiples of 2, 4, 6, 8, and 100, and so on. Then come to 3. 3 is a next prime number. Cross out all the multiples of 3 the same way. Then come to 5, and same thing. Circle 7. 6 is a composite number. And circle 11 and cross out its multiple. So if, remember that table 1 through 100, if we do that, this is what we get in all of our, these are the prime numbers between from 1 to 100, meaning these numbers, any of these numbers that are circled, let's take 67, can only be divided by itself or 1, and you will have no remainder. Others, I mean, they will have, I'm sorry, they can only be divided, but yeah, it will have no remainder, but only if it's divided by itself or 1. But the other ones like 66, you can divide it by 66, and you can divide it by 1, and you can divide it by 2, you can divide it by 3. So it has, it's not a prime number because it has other options for division. And this is called sieve of Eratosthenes. Eratosthenes was a Greek mathematician from Greek in 3rd century BC. Okay. Now, one of the important things in math is factor tree. Every composite number can be expressed as a unique product of prime numbers. And we use factor tree to find prime factorization. To find the prime factorization of a number, you select any 2 numbers whose product is a number that you want to be factored. If the factors are not prime numbers, you have to continue that factoring each composite number until you get all the factors that are prime. Let me give you an example to make sense of what we're talking about. 210, that's a composite number. It's not a prime number. So we can, when we talk about factor tree, this is called a factor tree. It's a product of 2 times 105. Now, 2 is prime, so I just leave it alone. But 105, is a product of 3 times 35? Now, 3 is prime, so I just leave it alone. 35 is a composite number because I can have 5 times 7 and get 35. Now, these are 2, 3, 5, and 7. These are factorization of 210. Or 210 can also be a multiple of 14 and 15. Again, notice, doesn't matter which way I go, I end up with the same factorization, 2, 7, and 3, 5. 2, 7, and 3, 5. Okay? You can do prime factorization by division. That's a little bit time consuming, but you can do that too. I mean, you got to do that if you have large numbers like 34,200 divided by 2, then you take the quotient again divided by 2, and you keep doing that. Now you come here, you divide it by 3, divide by 3, divide by 5, and 95 divided by 5 is 19. This is prime, and you stop. You see, these were not prime. These were composite. That's why I kept on going till I reached a prime number. So these numbers in blue, they are prime factorization for 34,200. All right. Now, we got a couple of things, what is called greatest common divisor, or GCD. GCD of a set of natural number is the largest natural number that divides without a remainder every number in that set. For example, we want to find the GCD of 12 and 18, okay? Divisors for 12s are 1, 2, 3, 4, 6, and 12. By divisor, I mean you can divide 12 by any of these numbers here, and you get no remainder. Divisor of 18 are 1, 2, 3, 6, 9, and 8. So I write these two as a set, and you see now the importance of learning what is a set. Then I look at them, and I see what is common between them, because we are looking for greatest common divisor. That's, remember in the last lesson, that's where the intersection comes from. So we see what's common between both of them. These are the common number, 1, 2, 3, and 6. And then I choose the one that is the greatest in value, which is number 6. So 6 is the GCD for 12 and 18. What that means is this, that you can divide a 12 by 6 and 18 by 6, and you will have no remainder. If you go if you go to 7, if you go to 9, for example, 18 can be divided by 9 and there's no remainder, but 12 can, if you divide 12 by 9, you will end up with a remainder. So the GCD is 6. Don't worry if these are too much and you can keep them in your head. As you practice, these become familiar to you. Now, if you want to find GCD of 2 or more numbers, you got to find prime factorization, like what we did in the previous slide for 12 and 18. The list each common factor with the smallest exponent that appear in each the prime factorization, then determine the product of the factors found in the steps in step 2. Let's look at an example. Example 3 and 4 on page 232 and 233. Let's go there. Okay, I think the textbook is clear. So if you look at your textbook on page 232, 32, we want to find the GCD for, or prime factorization for 216 and 200. Actually, we want to find GCD, but in order to do that, first we need to do prime factorization, meaning we keep finding products of the numbers that if you multiply them, you get that number, but we will keep going on until all the numbers that we get are prime numbers. Like 216, if you look at your textbook, it can be product of 2 and 108. Now 2 is prime, so I leave it alone. 108 is a product of 2 times 54. Again, I leave 2 alone. 54 is multiplication of 2 times 27. 27 is multiplication 3 times 9. 9 is 3 times 3. So I get, in those blue oval shaped things, you get the prime factorization for 216. Now notice then the textbook writes it 216 is equal. How many 2's we have? 3 of them. So it's 2 to the power of 3, or 2 with the exponent 3 times, and we have 3, so 3 to power of 3. So we got the prime factorization for each of them for 216, and we wrote it with proper exponent. Now we do the same for 234, the same process, and we see that all the primes are 2, 3, 3, and 13. So we write 2 times 3, we got 2 3's, so 3 to power of 2 times 13, okay? So now in order to find the GCD, the third step is you want to find the greatest common divisor for these two numbers. You picked those prime numbers that are common. There are 2 and 3, and you pick the one when you pick them, you pick them with the least common denominator, with the smallest common denominator. You see, I have 2 in 216 with the power of 3, and I have 2 in 234 with power of 1. I pick power of 1. And I have 3 to power of 3 and 3 to power of 2. I pick power of 2. So the GCD is 2 times 3 to power of 2, or 18. Is that clear?
Yeah. Yeah.
Okay. Now, the same thing on page 233 for numbers 40 and 24. 40 can be written as a product of 10 times 4. 10 is 5 times 2, and 4 is 2 times 2. So I get all the prime factorization. 24 can be 2 times 12. 12 is 2 times 6. 6 is 2 times 3. So I get the prime factorization for 24 too. So I write the factor 3 tells me that 40 is equal to 2 to power of 3, because we have 3 of them, and times 5 to power of 1. And I do the same thing for 24. Now I look at what's common between both of them. It's only 2. And the exponent, the power is the same. So the GCD is 2 to power of 3, or number 8. What that means is this, that if you divide 40 by 8 or 24 by 8, you get no remainder. But if you go even let's go to 10. 40 divided by 10, yes, you get no remainder, but 24 divided by 10, you get a remainder. So that's not 10 is not a GCD. 8 is the largest number that you can go, is the greatest common divisor for both of them. Okay? All right, let's move on. Another very important thing that comes handy is a least common multiple, or LCM. The LCM of a set of natural numbers is the smallest natural number that is divisible without a remainder by each element of that set. For example, we want to find the LCM of 12 and 18. Okay, what are the multiples of 12? Well, 12 times 1, 12, times 2, 24, times 3, 36, and go on. We get to 144. Multiples of 18, 18 times 2, 36, and if you keep going on, and then you look at them and you see the common multiples are the ones that are in bold. They are 36, 72, 108, and 144. The least common multiple is 36. That's the smallest number that is divisible by both 12 and 18 and with no remainder. If you go, for example, let's see, any less than that, if you go to 24, well, 24 divided by 18, you will end up with a remainder. Or if you go by 18, 18 divided by 18, there is no remainder, but 18 divided by 12, you will end up with a remainder. So the LCM is 36. All right? Now, when we want to find the least common multiple of two LCM of two or more numbers, first we need to find the prime factorization, then list each prime factor with the greatest exponent that appears in any of the prime factorization, and determine the product of the factors found in step 2. Let's look at an example. These things make sense when we see an example. Again, from your textbook, if you go to page 234, example 5, it says find the least common multiple for 144 and 300. Okay, 144, when we do the prime factorization, is 2 to power of 4 times 3 to power of 2. 300 is 2 to power of 2 times 3 times 5 to power of 2. How did we get those? We use that prime factorization speed. That's how we get them. And then we select every prime factor that occurs raised to the greatest power to which it occurs in this factorization. So we get 2 to power of 4 times and 3 to power of 2 and 5 to power of 2. Okay, then we find the product of that. So we look at both of those factorization, and then we select each prime factor with the greatest exponent. There is a 2 in both of them, but we choose 2 to power of 4. We go with the largest exponent. Or there's a 3 in both of them, but we choose 3 to power of 2. And then when we multiply it, we get on page 235, you have the answer. The product is 3600. That's the least common multiple of 144 and 300, meaning if you divide 3600 by 300 or divide it by 144, you will end up having no remainder. Okay. One example that how this can be used in a real world problem is example number 6. It says a movie theater runs its film continuously. One movie runs for 80 minutes, another second one runs for 120 minutes. But if both movies start at 4 p.m., when will be the movies begin again at the same time? Because you see, they have different lengths. But again, at some times in future, there will be a time that both of them start at the same time. We want to find that. We want to, in other words, we want to find the least common multiple. So we do the same thing. We factor 80 and we factor 120. We picked all those prime numbers with the largest exponent. 80 is 2 to the power of 4 times 5. 120 is 2 to the power of 3 times 3 times 5. So I pick 2 to the power of 4 times 3 to the power of 1 and 5 to the power of 1. And then you multiply these 240 minutes or in 4 more hours. So if it starts at 4 p.m., at 8 p.m., again, these two movies will start at the same time. You follow? Okay.
Oh, I was on mute. Yeah, I'm just trying to take it all in. It's just a lot of information, but
I know.
practice, it'll
yeah. The more you practice and do these examples, it becomes clear. Now, this is fun. This part is easier. We're dealing with integers. Remember we talked about natural numbers, counting numbers. Now, in integers, we can have negative numbers too, but there's no fraction. So integer, if you think of the number line that is here, the one from 0 going toward right, positive, and the one going left are negative. But no, you got to be careful about this part. -1 is greater than -2 because it's closer to the 0, which is the reference point. Okay. So these are positive integers. These are negative integers. These two are opposite. -4 and +4 are opposite of each other. And there is a space between them because to go from -4 to +4, you have to go 1, 2, 3, 4, 5, 6, 7, and 8. Okay. Set consisting of a natural number, 0 and negative of the natural number is called a set of integers. The number line is a graph we use to visualize the set of integers as well as a set of other numbers. This is called the number line, this thing here. Now we have also these symbols. This means less than, this means greater than. When we want to use for integers or any other number. For example, -4 is less than 3, so we must use this symbol. -1 is greater than -5. -5 is less than -2. 0 is greater than -3. You follow? Okay. Oops. Now, the absolute value of an integer, which is the symbol is, you put that integer with these two bars around it, is a distance from 0 to that integer, whatever that distance is, and it can never be negative. It just shows the absolute value of that number. So, for example, absolute value of -4 is 4. Absolute value of 2 is 2 because it shows the distance from 0 to that number. Now, the rules for addition of integers, these are very simple, or for addition or subtraction. Add their absolute value, the sign of the sum is the same as the sign of the two numbers, if they have the same sign. If the integers have different signs, subtract the smaller absolute value from the larger one. and the sign of the sun is the same as the sign of the number with a larger absolute value. And you can do regrouping. Two digits number often results in regrouping from other column. Let me explain what I mean. Let's say if you have -3 plus -2, what's the absolute value of -3 is 3. What's the absolute value of -2 is 2. Add them together, 5. What's the sign? The sign that you have here, -5. Okay, so it means if you're here -3, you go 2 more toward left, you end up here. Okay. All right. Now, if we have a situation like this, we have solve -1 plus -8. Again, you know, visually, this is a situation. -1 is here. We want to go add to it -8, meaning we want to go 8 more units toward left. So if I go 8 more units toward left, I'm going this way, end up -9. So I take 1 plus 8, 9, and the signs are the same. I just put the same sign. -1 plus -8 is -9. But let's say, for example, if 8 was plus, -1 plus +8 would be +7, because you're here and then you want to add 8 units going this way, going toward right. So you go 1, 2, 3, 4, 5, 6, 7, and 8, you end up at 7. Okay.
So if it was like -1 plus just 1, then it'd be 0.
-1 plus what?
Plus 1.
Oh, it would be 0, exactly, because they cancel out each other. Yeah. Now, rules for multiplication and division for integer is very simple. If they have the same signs, whether you multiply or whether you divide, the product is always positive. If they have different signs, whether you multiply or divide, the product is always negative, as you can see here. Again, let's okay. About exponential expression, exponent indicates repeated multiplication. Again, rules for multiplying real number can be used to evaluate exponential expression. For example, let's go to page 244 and look at the examples over there. For example, maybe use, oops, let me use my tablet. I think that can help better understand this problem. Okay, so, oops. Let me go to share screen. Okay. These are the things that you got to be careful. They're kind of tricky. For example, if you have -6 to power of 2, this means -6 times -6. And the rule is this: whenever they have the same sign in division or multiplication, you have positive. -6 times -6 is +36. Okay. But the second example, -6, the 2 is here. Notice the 2, the 2 is only for 6, doesn't include the sign. So it means minus times, I put a part, 6 times 6, which is 36, or minus 36. You follow?
Okay, so I think, okay, so I think where I'm getting thrown off.
Okay, you see, here I had 2 for in the, and then this parenthesis means this 2 applies to both 6 and also to the sign. So I have minus time minus.
Okay.
But here I have 2, the 2 only above for only for 6. So it's like minus parenthesis 6 times 6. 6 times 6 become 36, but this minus remains because the 2 doesn't apply to that.
So that's part of the answer then, since it doesn't apply to that.
Yeah. Let's look at another example. Minus 5 to power of 3. But notice I have this parenthesis. That means this 3 applies to both the sign and also to the integer that I have. That means this is equal to minus 5 times minus 5 times minus 5. Okay? Here, let's go one at a time. 5 times 5, 25. Minus times minus, plus. But then I have another 5 here. 25 times 5 is 75. And plus times minus is minus. So the final result is minus 75. Okay. All right. That's basically, you just have to remember where the exponent is. Is it for the sign, or is it for the integer, or is it for both? You just have to keep that in mind. So remember, any 2 numbers, any 2 integers that have same signs, if they are multiplied by each other, like here, the answer is positive. But if they have different signs, this is plus, this is negative, the final answer is negative, as you can see it here.
Okay, on that one, how are we getting 75 again? I'm sorry, I think I missed.
Because 25, you see, 5 times 5 times 5. 5 times 5 is 25. 25 times 5 is 75. Oh, I'm sorry. What did I say? No, that's not. 25 times 5 is 125. Sorry about that.
Okay, that's where I was wondering. I was like, wait a minute.
Yeah. I'm sorry. I apologize.
Okay.
No, I wasn't thinking.
So it is 125 then.
Yeah.
Okay.
Okay.
Yeah. Okay.
All right. Let's go. Okay, let's go back to our PowerPoint. Where am I? Okay, here. Okay, all right. 244, yeah, we did that. Okay. The divisions of integer, the same thing. When you divide with the same sign, you get positive. Negative divided by negative is always positive. But if you have mixed signs, plus and negative, then you get negative. Okay?
Okay.
Same sign positive, different signs negative. The order of operation is very important. When you perform all the operation within grouping symbol, within a parenthesis, then evaluate the exponential expression, then do the multiplication and division in order in which they occur from left to right and finally do addition and subtraction in order to in which they occur from left to right. This is the order of operation. Always take care of inside the parentheses, then exponent, multiply, divide, add, and subtract. There's an expression that says, please excuse my my aunt, what was it? Please excuse my dear Aunt Sally. You'll excuse my dear Aunt Sally. Now, for example, let's look at page 246 and 247. That's a very good example here. Oh, got to share a screen. Okay, now notice it has 8 divided by 4 multiplied by 2. Okay, we want to take care of this problem. So we go from left to right, from this way, that way. So 8 divided by 4 is 2. 2 times 2 is 4. Okay, so you don't do 4 times 2, 8, and 8 divided by 8 equal to 1. First, you need to go, you go from left to right, from this way to that way. And 8 divided by 4 is 2. Let's look at another one. Let me see, for example, example 7. We have 6 to power of 2 minus 24. Then, where is it? Divided by 2 to power of 2 times 3 plus 1. Okay, so we go from left to right. 6 to power of 2 is 36 minus 24 divided by what happened? Okay, divided by, okay, here I take care of the exponent. 2 to power of 2 is 4 times 3 plus 1. All right, so we go from left to right, and first we do the exponent before we do any other operation. Now, again, from left to right, from this way to that way, we have 36, so we have 36 minus, we have 24 divided by 4. See, we look at here, 24 divided by 4. 24 divided by 4 is 6 times 3 plus 1. Do you follow me? Okay, then 36 minus 6 times 3, 18, plus 1. So the answer would be 19, because, let me turn this off. The 36 minus, again, going from this way to that way, left to right, 36 minus 18 is 18, plus 1 is equal to 19. All right. You follow?
Yeah, I have a quick question. So, so the order of operations, so it's parentheses, exponents. So wouldn't multiply be next, or did we already do multiply when we did the exponents?
So it's, remember, please excuse my dear Aunt Sally. Please, so parentheses, exponent, how do we say? Let me write it. Please excuse my dear and Sally. So do the parentheses, then exponent, then multiply, then divide, then addition and subtraction.
Okay, I guess where I'm getting thrown off is that if according to that rule, isn't multiplication before divide, but I feel like we didn't do multiplication.
Oh, but remember that, you see, we go from left to right. We go from left to right. You see, let me see. If you go from left to right, what's the first operation? You got exponent minus 24 divided by 4. So from going left to right, the order is important. Division, the division comes before this multiplication here. That's why I did the division first.
Because it was the first one left to right.
Left to right. So remember the order here, that's important here, but keep in mind, left to right, left to right.
Okay. Yeah, that makes sense now. That's what was throwing me off, because I was wondering, like, why are we doing division before multiplication?
Oh, good point. Very good point. That's very good. Okay, so let's move on. Yeah, I think we don't need the tablet anymore. Let's go to the PowerPoint. So that's, let's see. Yeah, I think that's clear. So that's the little thing to remember. Please excuse my dear Aunt Sally. Parentheses, exponent, multiplication, division, addition, and subtraction, but from left to right. Don't forget that. All right. Now, rational numbers. A set of rational numbers, which is shown by Q, is a set of all numbers of the form P divided by Q when P and Q are integers and Q cannot be 0, because we don't divide a number by 0. Now, every rational number, when expressed as a decimal number, will be either terminating or repeating decimal number. What I mean is, either there's a decimal that ends, or it keeps going and going and all going, like the number pi. There are some rules about rational numbers and fractions. For example, if I did, this is called a fraction. The top is called numerator, the bottom is called denominator. If I want to multiply them, just multiply 1 by 2 and 2 by 2. Multiply the numerator and the denominator, and you get 2 divided by 4, which is same as 1 over 2, okay? Now we have positive mixed number and improper fractions. Actually, let's go to page 252 to make that more clear. Actually, from page 251, if you take a look at page 251, at the bottom of the page, it talks about mixed number and improper fraction. A mixed number consists of a sum of an integer and a rational number expressed without the set of addition or sign. For example, a mixed number it's like 3, 4 over 5. Do you see that in your textbook? Okay. The 3 is the integer, and the rational number is 4 over 5. That means 3 plus 4 over 5. And this is called a mixed number. Now, improper fraction is when the numerator is greater than the denominator. 19 over 5 is called an improper fraction. And you can convert the mixed number 3, 4 over 5 to the improper fractions. And if you go to the next page, Do you need to see that on a tablet, or is the textbook okay?
You know
I
what?
can do.
If you can do it on the tablet, it sort of helps me when you.
Okay, sure. Let's do that on a tablet. Okay. So for example, if they ask us convert a mixed number to the improper fraction, and remember, what was the improper fraction? A fraction that has a numerator greater than denominator. So this is a improper. This is a mixed number, 3, 4 over 5. It means 3 plus 4 over 5. This is an integer, and that's a rational number. If I want to convert that to an improper fraction, take 5 here, multiply it by 3. 3 times 5 be 15. Then add it to the numerator. 15 plus 4 is 19. Then so you write it, the whole thing becomes 19 over 5. You follow me?
Yeah.
Let me show you another one. Let's say, I'm sorry?
So we're just using it to find out the top number, but the 5 still stays on the bottom.
Yeah, exactly. If I have, let's say 2, 1 over 4, this is a mixed number. If I want to make it converted to the improper fraction, I take 4, multiply it by 2, and then add it to the numerator. 4 times 2 is 8. 8 plus 1 is 9. So I get 9 over 4. All right?
Yeah, that makes sense.
Okay. So let's continue. Let's go back. Okay, 250. Yeah, we showed that. We talked about this. A mixed number, I'm talking the same thing. For example, you have a mixed number is you have an integer and a rational number. Visually, if you have these 3 circles, you have integer 2, and then if you notice, only 1/4 of this circle is yellowed, so you have 2 plus 1 over 4. And it's the same as if you take 4 times 2 becomes 8. 8 plus 1 is 9. Is same as 9 over 4, because if you look at it visually, if you look at it, it's the same thing. You have 1, 2, 3, 4, 5, 6, 7, 8, and 9 of these division parts of a circle that are colored yellow, and 9 out of the 9 out of the and each of the circle is divided to 4. That's where the 4 comes from.
Okay.
I think we did that, page 252. Okay. Converting a positive improper fraction to a mixed number. Yeah, in other words, we are doing the opposite one. You divide the numerator by the denominator. You find the quotient and the remainder. The quotient that you got in step 1 is the integer part of your mixed number. The remainder is the numerator, and denominator will stay the same. In other words, here we are doing the opposite of what we did before. Before we went from a mixed number to the improper fraction. Now we want to go from improper fractions to a mixed number. Here, 7 over 4. That's an improper fraction. The numerator is greater than 4. 7 divided by 4, 4 goes to 7 one time. 1 times 4, 4. 7 minus 4 is 3. 3 is the remainder. So the quotient becomes your integer. The remainder becomes your numerator. And denominator, the denominator remains the same. So 7 over 4 is same as 1 3 over 4. And I think the examples on, it's the same thing in the textbook. It shows the same thing that we did here. Okay.
Yeah. I think I sort of get it. Is there any way you can do one example on the tablet? Just so.
Sure. No problem. Let me go here and clean up. Okay. For example, if we are having like an example 3 of our textbook, page 252. Okay. It says convert 47 over 42 over 5 to a mixed number. This is an improper fraction. We want to convert it to a mixed number. So we do the division. 42 divided by 5. 5 goes to 42 8 times. So you get 2. So here is this is my quotient. This is my remainder. And this was the divisor or the denominator. So your quotient becomes the integer. So you put 8 here. The denominator stays the same. Your remainder becomes the numerator. So 2 goes to the top. The denominator is the same. And you have also your quotient becomes your integer. Does that make sense?
Yeah, that makes sense.
Okay. All right. Okay. Let's go back. Same thing that they did here. They took 7 divided by 4. 4 goes to 7 one time. Minus 4, 7 minus 4, 3. So the remainder becomes the numerator. The denominator is the same. And your quotient is your integer, the whole number. Now, when you do multiplication of fraction, again, simple. You just multiply the top and the bottom. If you have 2 over 5 times 3 over 4, just multiply 2 times 3 is 6. Multiply 5 times 4 is 20. So you get 6 over 20. And you can simplify it. 6 divided by 2 becomes 3. 20 divided by 2 becomes 10. Okay. All right. Division. Now, the trick about division that makes it simple is this. If I'm dividing 4 over 5 divided by 2 over 3, the thing is this. Just make that 4 over 5 times and then invert the 2 over 3. Make it 3 over 2. You see that? And then do the multiplication. 4 times 3, 12. 5 times 2, 10. 12 over 10. Now notice here, 12 over 10 is an improper fraction. So I divide it. I want to make it as a mixed number. 12 divided by 10. 10 goes into 12 one time. And 10, 1 times 10, and then you have a remainder of 2. You have 2 over 10 which I simplify, becomes 2 divided by 2, 1. 10 divided by 2 becomes 5. Do you follow, or do you want I can show it to you on the tablet if you want.
Yeah, if you can show me the simplification of that fraction.
Okay,
I
sure.
understand what you're saying, but I sort of, when I visualize it, it helps me.
Sure. Let me just write it down.
That rule of inverting the numbers, that always applies for division and fraction.
Yeah. So let me go to the tablet. Okay, so we have 4 divided by 4 over 5 divided by 2 over 3. When you have that, always make it that's same as 4 over 5 times, and then invert this, 3 over 2. Okay? And that becomes 4 times 3, 12. 5 times 2 is 10. But this is a improper fraction. I want to make it into a mixed number. So I divide 12 by 10. 10 goes into 12 one time. 12 minus 10, I get a remainder of 2. So remember, this becomes your integer 1 over, the denominator stays the same, and 2 becomes your, the quotient, the remainder becomes your, numerator, the denominator stays the same. But I can simplify this. 2 divided by 2 is 1, and 10 divided by 2 is 5. That's why I get the final result. Okay. All right. Let's continue. So did you follow me here?
Yeah, it makes sense.
Okay.
It's just a lot of information. I just got to practice.
Yeah, you got to do that. Yeah, sorry about that. Okay. Then if we want to add fractions, before adding them, we have to find their common denominator. And it's another name for common multiple of the denominator. And we find the lowest common denominator. To add or subtract fraction with a common denominator, we add or subtract their numerator and retain their common denominator. When we write a fraction with common denominator, we use the fundamental laws of rational numbers. Now, what do I mean here? You have these two fractions, 1 over 3 plus 3 over 4. Okay, we want to add that. So first, just look at the integer. Add 2 plus 3, you get 5. Then we deal with the fractions. 1 plus 3 over 4. Before you add them, you got to find their common denominator. You got to make their denominator the same. And the way to do that is you multiply the top and the bottom of the first fraction by this denominator, and the top and the bottom of the second fraction by the denominator of the first fraction. I multiply 1 over 3 by 4 over 4, because 4 over 4 means it is equal to 1. So I'm not changing the value of the fraction. You follow me? And 3 over 4, the second fraction, I multiplied by this denominator, 3 over 3. When I do that, notice the denominator of the two fractions become the same, 12. So now I have 4 over 12 plus 9 over 12. And all you have to do right now is just right, just write the denominator and add the numerator. Would be 4 plus 9, which is 13. Okay? So far, are you clear so far?
On that one.
Up to this point, don't worry about the rest.
Okay, so 1 times 3, 4 times.
All I did was I just took these two fractions and I made their denominator the same. And to make the denominator the same, I multiply the first fraction, both top and the bottom, by 4, and the second fraction, top and the bottom, here by 3. So I get 12 and 12.
Okay, I got it.
And then I just add these two fractions. They have the same denominator. You just add their numerator. 4 plus 9 becomes 13. Is that clear so far?
So far, yeah.
Okay. Now we go to the next part. Now we have, this is a improper, fraction. 13 is greater than 12. So we do the division. 13 divided by 12. 12 goes to 13 one times, the quotient 1. 12 minus 13 is 1. The remainder is 1. So you get 1 over 1 over 12. You follow?
Yeah, I have a quick question. Okay, so on 4 plus 9, I get it, it's 13. Why isn't it 12 plus 12 equals 24? Why does it say?
No, we don't want to do that. But we did the whole thing. You see, the rule is this. We did the whole thing to make their denominator the same. We don't add their denominator. If it was just adding the denominator, we didn't need to do this. We just add 3 plus 4. But we don't do that. The reason I converted them to same denominator is that so that I can add their numerator. Now you see you have a fraction saying 4 out of 12 whatever plus 9 out of 12 whatever, whether we are talking about apples or whatever, we are talking about cars, or it's the same as 13 over 12 whatever.
Okay, I get it now. Okay.
And do you follow how I get from 13 over 12 to here?
Yeah, you're basically doing what we were doing before. Right?
Yeah. So now you have 1 over 12 plus, remember, we had these integers, 2 and 3, 5, plus 5. So just add the integers. 1 plus 5 is 6, and then write the fraction next to it.
And we would keep it like that. We wouldn't try to
just keep it like that. Yeah. Okay. Now, the irrational number are the decimal number that keeps going, like the number pi. Irrational number is a real number whose decimal representation is non-terminating and non-repeating, like pi. It's not that the number keeps repeating. I mean, there's a repetition of number, but not in a same pattern. You just randomly. Now we come to issue of square root. Again, under irrational number. Actually, I prefer to call this, this symbol is called radical sign, and this is called, I prefer, the textbook uses the term principal square root. I prefer not to use the term square unless the number here is 2. And when nothing is written here, then you can say square root. But sometimes you can have other roots. But for the sake of simplicity, let's call it principal square root. And then this sign is called a radical. Now, let me explain. Let's say we have these irrational number. A radical square root n, and the same square root of n square root of b. When you have the same square root and you're multiplying, or if you're dividing, both multiplication and division, just write one big radical sign with the same square root and multiply the two numbers. If you're dividing, the same thing, just because they have the square roots is the same, the principal root is the same, just write one radical with that principal root and divide those two numbers. Okay? Now, provided that b is greater than 0 and a is greater than or equal to 0. Same thing. Okay. Now, let me, square roots, we can simplify square roots, we can divide, add, and subtract. Let's look at these on page 266, 267, and 268. On our textbook, if you go to page 266, for example, let's look at example number 1. If you see that on page 266 on the bottom of the page, it says simplify if possible. So you have square root of 75. Now 75 can be written as 25 times 3. Okay? Now what is 25? 25 is 5 times 5, or 5 to power of 2. When you have 5 to power of 2, that because it has a power of 2, it can come out of, it comes out of the radical sign. Do you want me to show that from the tablet? Probably would be easier. Let's go there. Let me show you. For example, it talks about simplify, and it gives us, okay, where is it? Okay, square root of 75. Now, remember, if there's no number here, it means it's assumed that it's 2. That's why we call it the square root. Okay, and it means, for example, square root of 25, it means is equal to 5. Why? Because 25 is 5 times 5, and 5 times 5 is 5 to power of 2. And if that goes under the radical sign, this exponent divided by this is equal to 1. 2 divided by 2 is 1. So 5 comes out of the radical sign, becomes 5. Do you follow me? Let me show you another example. If I had a square, let's say, it's not in the textbook, I'm just saying it myself. If I had 5 to power of 4, for example, all right? Take that exponent, divided by this principal root 2. 4 divided by 2 is 2. So 5 comes out of the radical with the exponent of 2. Okay? You follow? All right. So let's go back here. We have 75. 75 is, you can write 75 as 25 times 3. Okay. 25 can be written as 5 to power of 2 times 3. Now, this 2 divided by the 2 here, which is not written, but it's assumed, 2 divided by that 2 becomes 1, and 5 comes out of the radical sign, and you get this. 5 radical sign 3. So the final answer is this.
Okay.
Let's do another one. Let's say it has a simplify a square root of 500, okay? 500. Now, 500 can be written as 100 times 5, okay? 100 can be written as 10 to power of 2 times 5. All right, now this 2 gets divided by the 2 which is here, but it's not written. So 2 divided by 2 becomes 1. 10 comes outside. Radical sign 5. That's the answer.
Okay.
All right. Let's look at, let's look at page 267, example 3. Here, well, actually, let's look at example 2, example of a multiplication. Square root of 2 times square root of 5. You see, that's simple. They have the same principal root, so you write it as 1 square root 2 times 5, 10. That's it. Okay. If I have, notice this next one. If I have a square root of 7 times square root of 7, okay, 7 times 7 is 49, or 7 to power of 2, right? Now, but now, this 2 here can be divided by the principal root here, and 7 comes out, so the answer, the final answer is 7. All right. Let's do example 3. Let me close this. Okay. We have square root of 75 divided by, the square root of 3. And again, since they have a same principal root, which is 2, it's not written, but it's assumed. You can write that as 1 radical sign 75 divided by 3. And 75 divided by 3 is 25. Okay? And 25 is equal to 5 to power of 2. Again, 2 gets divided by the principal root here, comes out, so the final answer is 5.
So that last piece that you're doing right there, where it's 5 square root and then divided by 2, we always do that at the end to get the final.
If I can.
Okay.
Sometimes I may not be able to. But if I can, I do that.
Okay.
All right, let's look at page 268. Let's see what we have over there. Okay, let's look at example 4 and 5. For example, in example 4, it has A has 7 times square root of 2 plus 5 square root of 2. We want to add these two. Okay, so what do? We factor. You see, this is called factoring. Square root of 2 is common between both of them. So I factor out the square root of 2, and I get 7 plus 5. Do you follow me? And that is equal to a square root of 2 times 7 plus 5, 12. Or, in other words, 12 times the square root of 2. All right, let's look at another one. Let's see, for example, okay. Let's look at the B on example 4. 2 square root of 5 minus 6 square root of 5. Again, I factor out these square roots from both of them. It becomes, so I put a parenthesis here, square root of 5, I write it here, and I get 2 minus 6. 2 minus 6 is minus 4 times the square root of 5. That's the final answer, minus 4. Okay. All right.
Yep.
Let's do one from, and if you need to take a break, we can, after this, we can have a break. Let's do 2 more and then we take a break if you want to. Example 5, you have a square root of 2 plus square root of 8. Now, here, square root of 2 plus 8, I can write it as 4 times 2, which that becomes 2 to the power of 2 times 2. This 2 comes out, so it becomes 2 times a square root of 2. You follow so far? Then I have one square root of 2 here and another square root of 2 here. So I factor them out. I get 1 plus 2 times a square root of 2. Where did I get that 1? That 1 comes because when you factor, you're dividing. When I divide a square root of 2 by a square root of 2, I get that 1. Okay, so it becomes 3 square root of 2. That's the final answer.
Can you do another one of those? Because I think I get it, but
Of which one? The
did right now that like
the one that I just did?
yeah.
Okay, sure. Let's do the B one. For example, you have 4 square root of 50 minus 6 square root of 32. So you see, I look to see how can I make factor something from these square roots. Okay, I see I can write this as 4 times 25 times 2 minus 6 times 16 times 2. Okay, then this is 4 times 5 to the power of 2 times 16, 4 to the power of 2 times 2. Okay, you follow me so far? Okay, now these can come out, okay, because they have square root of 2. All right, 2 divided by 2 becomes 1. So it becomes 5 comes out, but it must be multiplied by 4. So you get 4 times 5, the square root of 2, minus 6 times 4, a square root of 2. Okay, you follow me? Then 4 times 5 is 20, the square root of 2, and 6 times 4, 24, 24, square root of 2. Okay, then I can now, I'm sorry, this should be 2. Now I can factor the square root of 2. Okay, so I factor square root of 2 out. I get the square root of 2, parentheses, 20 minus 24. So I get minus 4, the square root of 2. Follow? Let's do one division also so that we understand that before then we take a break. Example 6 talks about 15 divided by the square root of 6. Okay, so I multiply, in order to solve that, I multiply both this, in this fraction, I multiply the top and the bottom by square root of 16. Okay. This is equal to the square root of 16 times the square root of 16. The square root, the radical signs goes away and 16 comes out. Okay. And then at the numerator, I have 15 times the square root of 16. Okay. Now, remember, I can simplify that because 15 can be written as, 16 can be written as 4 to the power of 2. All right. Let me see, 4 to the power of 2. What did I do? Wait a minute. 15, 6. No. Something. No. This is not 16. It's 6. Sorry, I made a mistake. Sorry, this should be 6, not 6. Let's do it again. Sorry. So I have 15 over square root of 6. I want to do this division. I multiply the top and the bottom by square root of 6. That comes, the square root of 6 comes out and becomes 6, and I get 15 times square root of 6. Okay. Now I simplify that. 6 divided by 3 becomes 2, and 15 divided by 3 becomes 5. This is the answer. Okay. All right, then let's just see where we are in our PowerPoint. And yeah, let's take a break, 5 minutes break, and come back.
Okay.
All right. I just, let me put that on pause. Yeah, okay. And let's go there. And okay, let me show you something in this graph, in this picture. You know, we talked about natural numbers. Those are like 1, 2, 3 going to infinity. If we add 0 to this number system, then we get the whole number. So whole number is greater than natural number because it has 0. If we add negative numbers and negative integers, then we get integers, you know, negative natural number. Then we add rational number, and then we have these irrational number, meaning it's the decimal, it's not terminating. It's keep on going. That all these together forms the real number. Remember, we talked about the universal set and all that. So our universal set is the real number, which includes all of this. Okay, let's move on. And, you know, there are 3 important properties of real numbers that we want to remember, because when we perform operation, we need to keep these properties in mind. If an operation is performed on any 2 elements of a set and result in element of the set, we say that that set is closed under that given operation. Now, there are 3 important properties to remember. And that is, the first one is commutative properties. In other words, you can add a plus b or b plus b. Or you can multiply a times b is the same as b times a for any real numbers a and b. This is called commutative property. Another one is associative property. A plus b parenthesis plus c is the same as a plus parenthesis b plus c. Makes no difference. Same for multiplication. Now, distributive properties, like I can distribute the value of a over b and c. A times parenthesis b and c is the same as a times b times a times c for any real number a, b, and c. Now, let's see these. Also, exponent and scientific notation. These are important. If you have an expression like this, 5 to the power of 2, 2 is called the exponent, and the 5 is called the base. We read 5 to the power of 2 as 5 to the second power, or 5 squared power. Let's look at a couple of these things on page 282 and 283. Okay, if you look at the page 282, that table 5.4 gives you these properties, the product of the rules. If I'm multiplying two numbers that the base are the same, but the exponents are different, just write the base and add the exponent. Maybe 282 and 283. Let's just go to the tablet. I think that can explain it better. All right. Like here, for example, if I have, where is this? Okay. 9 to the power of 16 times 9 to the power of 12. See, the base is the same. The base is 9 and the same. The result is you keep the base, add the exponent, 16 plus 12. So it would be 9 to the power of 28. Yeah, 28. I can see, did it right? Yeah, why did it write 9 to the power of 18 in the textbook? I think that's a mistake. You have to add it, not subtract it. 6 plus 12 is 18. I'm sorry, because I wrote it, because I have, yeah, I wrote 9 to the power of 16. Okay, it doesn't matter. The power rule, if I have 3 to the power of 4, parenthesis, to the power of 5, this is the same as 3 to the power of 4 times 5, which would be 3 to the power of 20. Okay? If I have division, if I have, for example, 5 to the power of 12 divided by 5 to the power of 4. Again, notice the base are the same, 5 and 5. It's the same as 5, 12 minus 4, which would be 5 to the power of 8. Okay? Let's look at.
Subtract it when it's the division. We subtract the exponent.
Yeah. Provided the base is the same.
Okay.
Any number to the power of 0 is equal to 1. Any number. any B if any number to power of 0 is equal to 1. Remember that? Now, let's look at example 1. For example, and let's clear this here. Seven to power of 0 is 1. Number B, pi to power of 0 is 1. Number C, we have, well, I mean, these are the same thing. Oh, okay. The only difference, let's look at C and D. Minus 5 to power of 0. This whole thing, now notice this 0 applies to this whole thing. So it becomes 1. But look at number D. Number D is minus 5 to power of 0. This 0 only applies to the base, not to the sign. So that is equal to 1, but I have this minus sign here, so I need to put that here too. You follow?
Yeah. So anytime we get a power of 0, it's always going to be 1.
1, but be careful. Where is this power? Is it for the whole thing, or is it only for the base? It becomes equal to 1, but if it's like here, you got to keep the sign minus 1. It becomes minus.
But when it's in like in the parentheses, then it applies to both.
Sure. That's it about it. Yeah. Okay. Well, let me also mention. Oh, okay. We'll come back now. Let's go to the PowerPoint and we come back. Okay. So we talked about that. If we have, if you have a number to power of negative, any number to power of negative is equal to that 1 over that number to power of positive. Okay. Product rules of exponent, we talked about that. We did that. We multiply. We did that also. Division, we subtract. Multiplication, we add. These two, when you have like a parenthesis, these two get multiplied by each other. Okay, these are clear for you, yes? Okay, so now this is an important thing. We come to scientific notation. A positive number is written in a scientific notation when it's expressed in this form. This is called scientific notation. A is a number greater than or equal to 1 and less than 10. A is greater than or equal to 1 or less than 10. Because if it's equal to 10, then you have to add it to the exponent of 10. So it has to be less than 10. And n is an integer. Okay? So keep this in mind. Now we look at some example. I say it, then we will go and do the example on page 285. If the exponent is positive and you want to change scientific notation to decimal notation, move the decimal point in the number to the right, the same number of places at exponent. If the exponent is negative, move the decimal point in the number to the left, the same number of places as the exponent. Now, I know it doesn't make a whole lot of sense unless you see it. So let's go to page 285 and let's look at example 3, and let's do that on a tablet. For example, it says convert this scientific notation to decimal notation. This is a scientific notation. You have 2.6 times 10 to power of 7, okay? I want to change that to decimal. My exponent is positive. So I move the decimal point to this direction, toward right, from where the decimal point is, equal to the number of the exponents. So I have, the decimal point is here, I have to move it 7 times. So I have, it's here, then in the decimal point moves 1 time, it moves from here to here. That becomes 1, then 2, 3, 4, 5, 6, and 7. So that is 2.6 times 10 to the power 7. It's equal to 26 million. You follow what I did? Now, let's say if the exponent was negative, you have 1.1 times 10 to the power of -4. We do the same now in this time. Instead of moving right, we go left and put the decimal point. I have 10 to the power of -4. I move it 1 time, the decimal, which is here, moves here, this is 1. So I get 1, 2, 3, and 4. Then I put the decimal and the 0. So it's 0.00011. You follow? Okay. Let's go to page 286 and do example 4. Oops. Okay. And let's do that on the tablet while we are here. Saves us time. Okay. Here we have, now we want to do the opposite. We have decimal notation. We want to convert them to scientific notation. We have 4,600,000, and this is decimal notation. Even though I don't put the decimal, but I can put decimal here. But because it's 0, I don't need to write it. Okay. So I want to write that in a scientific notation. So what I do, I take this number here. I want to move this decimal here over there, put it here. So how many times I have to go? 1, 2, 3, 4, 5, 6. So I say 4.6 times 10 to the power of 6. You follow? Now, let's do one other way around. We have, oh, actually, no, that's, yeah, it's still the decimal notation. 1, 2, 3, 4, 0. 1, 2, 3, 4, 23. I want to make that as a scientific notation. So I want to move this decimal, which is here. I want to move it over here. How many times I have to go? But now, this time I have to put a negative exponent because I'm moving from left to right. This time I was moving right to left. Okay. This time when I move from left to right, I have to go 1, 2, 3, 4, 5. So I say 2.3 times 10 to the power of -5. Okay. Let's do number, okay. Let's do example 6 on page 287 also, while we are here on the tablet. Example, so multiplying numbers in scientific notation. I have 3.4 times 10 to the power of 9. I want to multiply that by 2 times 10 to the power of minus 5. 10 times 10 to the power of minus 5. Okay. So what do? I come and I can write this. Remember the rule of the associative rule that we discussed, those 3 properties that we discussed. These are all being multiplied by each other. It's like A times B times C times D. Doesn't matter. I can multiply A times D or B times C, and the order doesn't make any difference. So I say 3.4 times 2. I put this in one grouping, time 10 to the power of 9 times 10 to the power of minus 5. Okay. Now because that, and now here I can simplify this. 10 to the power of 9 times 10 to the power of minus 5. The bases are the same. I just add, or in this case, 9 minus 5, subtract. I get 10 to the power of 4. All right, times 3.4 times 2 is 6.8. So I get 6.8. Where am I? 6.8 times 10 to the power of 4. Okay, I simplify that. So I multiply them. I can even change it into a decimal format. This is a scientific format. This is, if I want to change it into decimal, all I have to do is, remember, I have to move this decimal point 4 times toward right, this way, that direction, because my exponent is positive. So I put 6.8, 1, 2, 3, 4. The whole thing is equal to 68,000. All right. Let's do one example of division. So we've done as much as we can with the tablet. Example 7, we have 8.4 times 10 to the power of minus 7 divided by 4 times 10 to the power of minus 4. Okay, remember we said when we have the base are the same, when we have division, you just divide this exponent, subtract this exponent from this exponent. So that becomes 10 to the power of minus 7 minus 4. Okay, which is the same as 10 to the power of minus 7 plus 4, because that minus time minus makes that plus, which is the same as 10 to the power of minus 3. Okay, so I got this part right. I got this part simplified. This whole thing is the same as 10 to the power of minus 3. Then I have to divide 8.4 by 4. By, it's simple. You can know it from memory. 8.4 times 4 is 2.1. Okay. So the final result is 2.1 times 10 to the power of minus 3. Do you follow me so far? Now, if I want to write it in a decimal notation, remember, notice this is negative. So I have to move my decimal point this way toward left because my exponent is negative. So I have to move it 1, 2, 3, and then put the decimal. So it would be 0.021. Okay, actually, well, yeah, or what did I do here? No, actually, I move it. Oh, I'm sorry, it moved 1, 2, and 3. So I need to have, yeah, it moves 1, 2, 1, 2, and 3. So I'm sorry, it kind of messy. It becomes 0.0021. Okay, you follow? I'm sorry, my graphic is not very good.
Yeah, I'm following.
Okay, now let's go back to our PowerPoint because I think we almost finished everything. Let me see. Yeah, we talked about these. We talked about converting decimal to not. We talked about those. We did exam page 28. We did that. Oh yeah, we finished. Just the last part, arithmetic and geometric sequences. If you look at page 294, you see a sequence in which each term after the first term differs from the preceding term by a constant amount is an arithmetic sequence. For example, if you look at page 294, example 1, you have 6, 10, 14, 18, 22, and goes to 26. From the first element to the second element, the difference is 4. Then again 4, and again 4. Each time it moves by 4. The difference, the amount that each one differs from the previous one is called the common difference, which is 4. I think that's basically all it is. Example number 2, it gives you 5, 3, 1, and -1. Each time is going 2 units down. So you go 5, then you subtract 2 minus, you go 3, then you go 1. From 1, again, if you subtract -2, you go to -1. You follow? Okay, and this is called an arithmetic sequence, and the difference between each element is called the common difference, when the difference stays constant. All right, any questions? Then if you don't have any question, we're done.
Yeah, no, I think, yeah, I know it's a lot of information, so I think I'm just gonna have to just practice it, and I might end up having to just review this video again, and just that's how I'm gonna end up getting it.
Sure. And you're doing good. All of you guys are doing good, and just pay attention to those little things that don't throw you off, but you just keep studying, keep paying attention to those little things, and you will do great. Okay, and again, if next week you couldn't make it, don't worry. It's Thanksgiving, so don't worry about anything.
Yeah, I'll send you an email. I might not be able to, but I'll send you an email.
All right, no problem. All right, take care and have a good Thanksgiving if I didn't see you.
All right, you too, Professor. Thank you.
All right, take care. God bless. Bye.